Hello, in this video, our objectives is to use the definition of these eigenvalues and eigenvectors to prove questions in further mathematics. So let's try to look at this example here. Show that this is taken from the past papers, and that is 3 marks. Show that if E is an eigenvector of the matrix M with corresponding eigenvalue lambda, and if K is a real number, then E is an eigenvector of the matrix Kn with corresponding eigenvalue K lambda. So what we're going to do is just simply to analyze this one line by line. It says show that if E is an eigenvector of the matrix M with corresponding lambda eigenvalue lambda, what we're going to do is to write it as a definition. So M, the E is an eigenvector of M, and the corresponding eigenvalue is lambda. So that is the statement number 1. Alright, so you're gonna get a mark for that one, for analyzing the first sentence there. And if K is a real number, so there is a K that belongs to a real number, then E, so what do you want to prove? Alright, so you must prove that what? You must prove that E is an eigenvector of the matrix Km. So what does it mean? That Km of E is equal to the K lambda of E. So this is the one that you're trying to prove. Alright, that is the one that you're trying to prove. Actually, to prove this one is not that difficult. All you just need to do is to play with the definition of the eigenvalues and eigenlambda. So what we need to do is just work into, from your definition, you need to simplify this, or you need to play with this and take the right hand side. So let's try to look at the left hand side. So let's look at the left hand side, and then we need to show that it's going to be equal to that. Okay, so ME, alright, you want an expression for K, so meaning we need to multiply that one by our K. So therefore, this one will give you K of ME. However, ME is equal to, since ME is equal to lambda E, so therefore, this is going to be K of lambda of E, which is actually the right hand side. So what does it mean is that we have already shown that KME is equal to K lambda E, and that one is 3. Right? It's not that complicated. It's very easy. But what's the meaning of that? What is the geometrical meaning of that one? It means that if the matrix M transforms E, alright, if the matrix M transforms E, and you multiply the M by a certain real number, by 2M or 3M, so the eigenvector does not change. Okay, the eigenvector does not change. What's changing is only the eigenvalue. So meaning if for example you have there 3ME, let's say that is 3ME. So the changes in eigenvalue will be 3 times of the initial eigenvalues that you have times the vector E. So the vector E does not change. So even, for example, you multiply by this matrix, multiply the matrix by 100M, the eigenvector will not change. Only the eigenvalue will change. Alright? Only the eigenvalue will change, but the eigenvector will never change. This phenomenon is very, very important as you go on to the next topic, which is all about diagonalization. Right? Diagonalization. However, before we proceed to this topic, so let's try to have one more example of proving question. Then after this proving question, we will have example on how to find the eigenvalues and eigenlambda. Again, for the definition, for proving, all you just need to do is to play to solve it is just to play with the definition, manipulate it. So, for example, the vector E is an eigenvector of the matrix A with corresponding eigenvalue of lambda. So what's the implication of that? So you just need to write this in the definition. It says lambda of x is equal to lambda of your x. And that is the meaning of that first statement. Right? And x also is an eigenvector of the matrix B. Now there's another matrix B, but with the same eigenvector. So meaning that's going to be B of the vector x. However, the eigenvalue is denoted by mu. So like that. Okay? So again, for you to be able to prove this kind of question, you just need to write the definition based on the statements given. So the first sentence means this. The second sentence or the follow-up expression means that one. What are we trying to prove? You need to prove that x is an eigenvector of the matrix PAQB. What does it mean? It means that if you have P times the A plus Q times the B, that x is an eigenvector of this. And how shall we know that it is an eigenvector of this? If we can make this equal to P lambda plus Q mu times the vector E times the vector x. Sorry. Right? So this is what are we trying to prove. This is the one that what we're trying to prove. So how shall we do that one? You need to use this basic premise that you have, that if f is the eigenvector of A and eigenvector of B, and lambda is the eigenvalue of A and mu is the eigenvalue of B, then you can get this one. So meaning, let's start with that solution there. Okay, so let me just pull it up again. And we need you just need to work on the left hand side, and then you need to get the right hand side. So we need this matrix A to be multiplied by your eigenvalue. So that's going to be P, your eigenvalue, P is a real number, times AX, right? And what is that one? That is equal to P of lambda of your x. Again, this one is already a proof that when you multiply a matrix by a real number P, the eigenvector is not changing, it's only the eigenvalue is changing. And the change of the eigenvalue is always proportional to the change of the P, to the change of the matrix here. And similarly on this B, you multiply that by your Q. So therefore you have Q of B of vector x. That's equal to, this is going to be mu x there. That's equal to Q of mu of your vector x. And then this one tells you that you need to add them up. So therefore this and this needs to be added. So you have your P of A of vector x plus you have your Q of B of vector x. Then what is this all about? The x is common, and as you can see, it's almost similar to that. Right? But what is that? You just also need to add this too. So P lambda of your vector x plus Q mu of your vector x like that. And then now you can factor out the eigenvector x. Then you have the P of A of vector, I said I want to factor that out. So of that vector x there. And then this is going to be P lambda of Q mu of your vector x. And there you go. That is actually your right hand side. Alright? So therefore by doing this one, we have shown that the eigenvalue of this one is P lambda plus Q mu. Now, again, what is the implication of that? In the first one, we have said that the eigenvector does not change even you multiply the matrix by a real number k. Alright? That is for individual matrix. But here it tells us as well that if you have two matrices with the same eigenvector, alright? Two matrices with the same eigenvector, and you multiply each matrix by P and Q that belongs to real number, the eigenvector will not change. It's only the eigenvalue that will change, and the changes follows whatever the changes into the matrix. Alright? So that is something interesting. Now, because a while ago we only have one matrix, and we said that the eigenvector does not change. But now we have two different vectors, two different matrices, and we're just trying to prove that if two vectors are added, the eigenvector will not change. Only the eigenvalue changes. If two matrices multiplied by two different real numbers, the eigenvector will not change. Right? So that is the message of this proving using the eigenvalues and eigenvectors. So in the next video, I'm gonna show you how to find the eigenvalues and eigenvectors. Thank you.